When we picture a mathematical space, we usually imagine a coordinate plane, a grid, or a measurable distance between 2 points. But at the absolute bottom floor of mathematics, space is defined without any concept of physical distance or geometric measurement at all. To build this foundation, mathematicians use a structure called a topological space. A topological space is a set of points paired with a specific collection of its subsets, which are called open sets. For a collection of subsets to qualify as a valid topology, it has to obey a strict logical rulebook consisting of 3 axioms. The first axiom requires that the collection must contain both the empty set, a set with exactly 0 elements, and the entire space itself. The second axiom dictates that the collection of open sets must be closed under arbitrary unions. A union is a set operation that combines all the elements from any number of chosen sets into a single, larger set. The third axiom states that the collection must be closed under finite intersections. An intersection is a set operation that isolates only the elements that multiple sets share in common. These 3 rules allow for absolute extremes. On one end is the discrete topology, where every single possible subset is classified as an open set. On the other end is the trivial topology, where the rulebook is applied so strictly that only the empty set and the whole space are considered open. These 3 axioms provide a perfectly rigid logical skeleton. They hold a mathematical structure together and define proximity and continuity completely from scratch, without requiring any reliance on human geometric intuition. We can test how these axioms work by applying them to a concrete, manageable case. Let's evaluate potential topologies on a simple 3-element set containing the points A, B, and C. This diagram shows 9 valid topologies on our 3-element set using overlapping ovals. Look at the complex arrangement in the bottom right. It satisfies all 3 axioms because any union or intersection of these inner subsets results in another subset already drawn within the collection. But not every collection of subsets passes the test. This diagram shows 2 specific collections of subsets on those same 3 elements that appear structured but fail the test entirely. We can see exactly the mechanism of failure for the right-hand example. If we take the union of the subset containing A and B and the subset containing B and C, we create a new subset containing all 3, A, B, and C. That larger, combined subset is completely missing from the designated collection, violating the second axiom. Space is a strict logical permission slip. If a collection of subsets fails to obey the union or intersection rules, the entire concept of the space breaks down. Explicitly drawing and listing every open set works perfectly for a 3-element set. But doing this for infinite sets is computationally impossible. To bypass this infinite complexity, mathematicians use a tool called a basis for a topology. A basis is a smaller, highly tractable subcollection of sets that acts as the core DNA to generate the entire massive topological space. A valid basis must meet 2 conditions. First, the basis elements must completely cover every single point in the given set X. Second, if a point lies in the intersection of 2 basis elements, there must exist a third basis element wholly contained within that intersection that also contains the point. By defining a valid basis, mathematicians guarantee the existence of an infinitely complex topological space without ever having to manually construct it set by set. We can apply these abstract basis rules to evaluate 2 different geometric shapes as foundational building blocks for a 2-dimensional plane. This diagram illustrates how overlapping circular regions successfully function as basis elements. Look at the lens-shaped intersection of the 2 larger circles. A third, smaller circle must be mathematically wedged inside that complex intersection to surround the point X. Contrast the circular basis with this diagram of a rectangular basis. Rectangles with sides parallel to the coordinate axes offer a massive architectural shortcut. Their intersection naturally forms a perfect rectangle. This renders the complex second basis condition completely trivial. This operational mechanic is summarized by Lemma 13.1. Every single open set in a topological space is simply a union of these chosen basis elements. Choosing the right basis optimizes the logical engine that generates the space, saving vast amounts of computational and theoretical effort. Once we can generate topologies efficiently, we face the next major problem: How do we compare two completely different topological structures imposed over the exact same set of points? A topology is defined as strictly finer if it properly contains all the open sets of another, coarser topology. Think of a topology as gravel. Smashing the pebbles into smaller, distinct pieces generates a finer, higher resolution topology out of the exact same material. The ultimate testing ground is the real number line. First, we have the standard topology. As this diagram shows, it is generated by a simple basis of standard open intervals between 2 points, A and B. Next is a strange competitor, the lower limit topology. This is generated by a basis of half-open intervals that strictly include the starting point, but not the end point. Finally, we have the highly complex K-topology. This is generated by standard intervals, plus intervals that explicitly exclude the sequence of fractions 1 over n, creating a cascade of missing points dropping towards 0. We have 3 completely distinct mathematical blueprints attempting to structure the exact same real numbers. We have to prove which blueprint creates the finest reality. Based on our basis lemmas, we can quickly verify one initial finding. Both the lower limit topology and the K-topology properly contain the standard intervals, making them both strictly finer than the standard topology. This sets up the ultimate tension. Between the lower limit and K-topology, which is finer, does one contain the other, or does the logic break down entirely? We attempt to fit a lower limit basis element inside a K-topology element. It immediately fails. The K-topology interval is punctured by 1 over n holes, so the solid lower limit interval cannot physically fit without colliding with those missing spaces. Attempting the reverse proof fails as well. Forcing a K-topology element centered at 0 into a lower limit element is impossible. The K-topology interval requires open space in the negative numbers, but the lower limit behaves like a brick wall at 0. By defining space through the strict logic of sets rather than physical metrics, mathematics allows for the creation of perfectly valid yet completely incompatible realities, all existing atop the exact same points.